the design example 320 from the course text. The objective is to design N-channel. You see over here, given the direction of the current. This is an N-channel JFET, and then you have a voltage divider consisting of R1 and R2. So you have to design a biasing circuit for the N JFET. So you have to design the circuit again with the voltage divider biasing circuit, which is shown in figure 61. So the part A is showing you the N-channel JFET circuit with the biasing circuit, and in part B you have the circuit with the DC analysis and the given circuit parameters for the circuit. Now, if you consider the figure 61A, the transistor parameters are given. The IDSS current with when VGS is 0 is 12 milliamps. Pinch off voltage is minus 3.5 volts. Modulation parameter is 0, which means we are considering an ideal JFET. Okay, that means if you are going to consider the drain current in saturation, when the transistor is in saturation, the drain current ID is not going to be affected by VDS. Okay, it's only the function of VGS and the pinch of voltage. It's independent of VDS, so we don't need to consider VDS. Now the constant that is given for the divider circuit is that the addition of two resistances R1 and R2 is 100 kilos. So you have to design the circuit such that the DC drain current is 5 milliamps and the DC drain to source voltage VDS is 5 volts. Okay, so VDS is your 5 volts. All right, and the drain current is supposed to be about 5 milliamps. So you have to design the circuit. By designing it means that you need to find those unknown resistances. What are the unknown resistances? You need to find R1, you need to find R2, RS is given, and you need to find RD, which ensures that the drain current is 5 milliamps for the given divider circuit, and VDS is biased at 5 volts. Okay, so we are going to check whether this VDS is greater than VDS SAT or not. So I mean, we can similarly, I mean, what we have talked earlier for MOSFET DC analysis, we can start with the assumption that this circuit biases the transistor in saturation region. So for that, the condition is that VDS should be greater than VDS SAT, right? If that is not the case, then we cannot use the IV relationship for the saturation region of the transistor. Okay, so to start with, let's assume the transistor is biased in the saturation region. So the DC current is then given by the relationship. Okay, you see there is no dependence on VDS because lambda is 0. So for this relationship, lambda is 0. Modulation parameter is 0. So what you have is you're given the pinch of voltage. You're given IDSS as 12 milliamps. ID is supposed to be 5 milli. So you can find VGS. Okay, so you can find VGS from this expression. It comes out to be minus 1.24 volts. Okay, now if you look at this circuit, you can find Vs. Okay, because you need VG. VGS is VG is the potential difference of gate and source. Okay, so this is VG minus Vs. So in order to find the potential at source, you see that the drain current, which is the same as the source current, you can write this. You can write the KVL for this loop, output loop at the source terminal of the transistor. So well, Vs is given by ID RS, and then you have another biasing, constant biasing, DC biasing of 5 volts, minus 5 volts. So you have to count for that as well. This is ID RS minus 5 volts. Okay, so this is written over here. Vs is ID RS minus 5 volts. ID is 5 milliamps. It's supposed to be 5 milliamps, and we are assuming that the transistor is biased in the saturation region. Okay, so let's plug the values. RS is 0.5 kilos. So this RS is 0.5 over here. This is 5 milliamps, and then you have this constant biasing of minus 5 volts. This gives you Vs of minus 2.5 volts. Now you have Vs. Okay, you know what VGS is. Then you can find the gate voltage. This gate voltage comes out to be minus 3.74 volts. Okay, this gate voltage is over here. This gate voltage is over here. Note that there is no gate current in a JFET device. So that's 0. Okay, we're not considering any input gate current. So the gate voltage that we calculated is minus 3.74 volts. And note that this gate voltage is the potential drop across the resistor R2. Okay, at this node, okay, that's the potential. So you can write this. You can find R2. You can find R2 by using the potential difference of these 2 points. So this point is at potential of minus 5 volts. So you can write this as Vg minus 5. Vg is now okay, and or you can use the voltage divider. I mean for example over here you see this is given by the voltage division. This potential is given by the voltage division due to this resistor R2. Okay, you don't need to even consider the current in the divider branch. So what you can do is you can write this as R2 over the addition of R1 plus R2, which is 100 Ks, multiplied by the potential difference between this point and this point, which is 10 volts. Okay, so then minus 5 is the potential over here. Okay, so again it's the you have the gate voltage. So from the gate voltage you can find what is the only unknown that you have in this equation is R2. Okay, so you can go ahead and find R2 as 12.6 kilo ohms from this expression. And if you have R2, then you can find R1 because R1 plus R2 is 100 kilos. R1 plus R2 was 100 kilos. So based on this specification, you have both the unknown resistances R1 and R2. You can see this specification was given in the question. Okay, so we are using this required specification. Now the drain source voltage can be obtained from the KVL. Now if you apply the KVL at this output loop, you can write this as 5 minus IDRD, the drop at this resistor. Okay, then you have the drop at VDS, then you have another drop at RS, which is 0.5 kilos, and then the difference of minus 5. So VDS is 5. You can see over here is 5 minus IDRD. You can take the VDS to the other side. Then minus IDRS minus 5. And then you see over here, you know what RS is. ID is 5 milliamps. So the only unknown that you are left with is RD. Okay, so you can reformulate the equation in terms of RD, and you can find the unknown RD as 0.5 kilos. Now, to check the analysis if we have done this correctly, we started with an assumption that the transistor is biased in the saturation region, and this is the saturation current of 5 milliamps. And we started off with the saturation expression. So now, if this expression is true, then VDS of 5 volts, which is given over here, 5 volts, should be greater than VDS set. Okay. If that is the case, then the above analysis is correct, and therefore the biasing distances that we found out are correct. So this should be greater than VDS set. And what is that? You know what the pinch off voltage is and what the gate source voltage is. So just you take the overdrive voltage, VGS minus V pinch off, which is minus 1.24 minus 3.5 is 2.26, which is still less than 5 volts. So 5 volts is greater than VGS minus VP. So it's just like the MOSFET. Okay, we were considering VGS minus V threshold, right? So for an N-channel JFET device, your VDS of 5 volts greater than 2.26 volts, which shows that JFET is indeed biased in the saturation region, so as initially assumed. So the analysis is correct, which means that the resistances that we have found out are all right. Okay, they do ensure the transistor is biased in saturation region, and you have a saturation current of 5 milliamps with VDS of 5 volts. Okay. Now let's consider another example. This is 3.21 from your course text, and the objective is that you have an independent current source of 0.8 milliamps at the source of a P-type JFET. Okay, so I can write this as P-type because the channel is P-type. Okay, This is p-type JFET. You can also look at the symbol. The direction of the current is reversed. In this case, it's like this. It's so it's going into the source over here, and look at the drain terminal. This is the source terminal. Okay, this is the drain terminal. The direction of the current has been reversed. If you compare this with the earlier symbol, the direction of current was like this. It was into this bar of the circuit symbol. Now it is coming out of that, right? So it is coming. The current is coming out of that. So the gate is biased at 1 volts, okay, and you're given a biasing current of 0.8 milliamps. So the objective is to calculate the quiescent current and voltage values in a p-channel JFET circuit. The parameters of the transistor in the circuit are shown in figure 63. This is figure 63. Okay, this is figure 63. So the parameters are given. You are given the, you can see that the RD is given, the drain resistance is given, gate voltage is given, the quiescent current is given. So IDSS is the transistor parameter 2.5 milliamps for VGS 0. Pinch off voltage is given, modulation parameter is 0. That means we are considering the ideal JFET. The transistor is biased with a constant current source. Okay, so from figure 63, we can write the DC drain current, because over here, if you consider the voltage drop at VD is the output voltage as well. So VD minus 9 volts divided by RD gives you ID. Okay, and this ID is supposed to be equal to your IQ. Okay, so the drain current which flows from the source to drain current is the same. So you can write this as ID equal to IQ, which is 0.8 milliamps, a constant current source biasing, and then VD minus 9 over here. You consider the potential difference in these 2 points, and what is the current flowing through the non-resistor RD of 4 kilos. Okay, so the current is 0.8 milliamps. So you go ahead and find what VD is. This gives you VD as minus 5.8 volts. So we know what VD is. Now again, let's assume the transistor is biased in the saturation region. Use the same relationship for lambda equal to 0. So this is an ideal case in which you have a constant slope in the saturation region like this. So in saturation, you don't consider forward resistance. ID is constant, irrespective of VDS. So okay, this is VDS and this is ID for a P-type MOSFET. Okay, and remember that for P-type MOSFET, V pinch off is positive over here. It's positive. Previously, V pinch off was negative for N channel. So you see V pinch off was negative for N-type JFET. Over here, to pinch off the channel, you need a positive supply. So not only the current directions and the polarities are reversed, even the pinch off voltage and the gate source voltage have different polarities. So okay, you plug those values of the quiescent current or the drain current. We have 0.8 milliamps. IDS is given as 2.5 milliamps, and pinch off is 2.5. This gives you VGS as 1.086 volts. And from this, you can find what VS is, because you know what the gate voltage is. The gate voltage is VG is equal to, VG is 1 volts. VG is set to 1 volts. So if VG is 1 volts, you know what VG is. So you can find VS, okay, from this expression. This is 1 minus VGS, which gives you minus 0.086. So you have VS, then VSD, which is the drop at the source and drain. VSD, since we evaluated VD first as minus 5.8 volts, then the difference of VS and VD is going to give us, VD is minus 5.8, this gives VSD as 5.71 volts. To check whether this analysis is correct, we again check whether it is in the saturation region or not by evaluating the overdrive voltage, V pinch off minus VGS. So pinch off is given as 2.5, VGS is 1.086, this is 1.41 volts. So this is your VSD, and VSD 5.71 volts is indeed greater than 1.41 volts, which verifies that the transistor is biased in saturation region. Assume our assumption that this biasing constant current source is the saturated current of the transistor is correct. Okay, so it means that the voltages that we have found out, analyze like we have found out VD, VS, assuming the transistor is in saturation, are correct.